we have section 11.1, parametric functions. Quiet, please. All right, tell me what you think of when I say the term parametric function.
Two equations that make up one.
Two equations that make up one. What else? Those are the, okay, those are the key things to remember about parametric functions. It's yet another way to graph a function or to look at a function, and in this case, we break the motion down into x motion and y motion based on a new parameter, which is most often time. Okay? So that's why we see equations like x equals cosine t and y equals sine t. This is equivalent to a rectangular function. Does anyone know what one is equivalent to? Very nice. It is. And what is that?
A circle.
A circle with a radius of 1. So if I were to graph x equals cosine t and y equals sine t on the interval from 0 to 2 pi, I would get the circle. Now I would need to think about whether I get the full circle or not, and that's going to be based on our interval on t, correct? If it gives us enough space to get all of the points for our x and y. All right, so the idea is, to graph this, we would plug in some points for t into each of our equations and plot an x and a y. Okay. All right. So in this problem, in this example, it says sketch the parametric curves and identify those which define y as a function of x. So how do we determine if something is a function? Vertical line test. All right. In each case, eliminate the parameter and find the equation that relates x and y directly. So if we look at what we have in A, we have x equals cosine t and y equals sine t, and our interval is from 0 to 2 pi. All right. Well, Boston pointed out that this is a circle with a radius of 1. And Boston, you want to tell us how you do that? You memorize that one. Well, it ties back to that identity that never goes away. Cosine squared t plus sine squared t equals what? 1. Well, if x is cosine t, then we can rewrite cosine squared t as what? X squared. And we can rewrite sine squared as y squared equals 1. This is the standard format for a circle. Centered at where? Centered at 0, 0 with a radius equal to 1. All right? So when they ask us to remove the parameter and write it as a function that relates x and y directly, that means we only want x's and y's in our solution. All right, is this a function? Not a function. Because it fails the vertical line test. Okay? So if you see a cosine and a sine in your x and y, this identity could be useful. All right, not always, but it could be. So it's something to keep in your toolbox. Let's look at B. Now, if A was a circle with a radius of 1, in B we have x equals 3 cosine t and y equals 2 sine t. What do you think that is? Yeah, an oval, an ellipse. And the ellipse has a stretch factor of 3 on the x-axis and a stretch factor of 2 on the y-axis. So again, I see a cosine in my x, a sine in my y. So I'm still thinking that my identity, cosine squared t plus sine squared t, equals 1 is going to be helpful. And how can I rewrite cosine in this case? Cosine t is equal to what? X over 3. And y over 2 would equal sine t. So our rectangular form would be x over 3 squared plus y over 2 squared equals 1. And you'll recognize that as the standard formula for an ellipse with a stretch factor of 3 on the x and a stretch factor of 2 on the y. Okay? Something to keep in mind in A and B and C is the interval. They told us t equals 0 to t equals 2 pi. Well, if we're graphing this y in terms of x, I need to know the x value. So when t equals 0, x equals what? Cosine of 0, which is 1. And here, x equals cosine of 2 pi, which is what? Also 1. All right, so they're saying start at 1 and end at 1. So we get our whole circle. All right, and now here, 0 to 4 pi, t equals 0 to t equals 4 pi. And we have x equals 3 cosine 0, which gives us what? 3. And x equals 3 cosine 4 pi, also 3. Beginning and ending. All right, let's take a look at C. In C we have x equals root t, and y equals t minus 2. No sine, no cosine. So what shall we do here? Yeah, we want to replace this t with our x. So t is equal to what? X squared. So this becomes y equals x squared minus 2, which is a parabola. But again, they said we're going from t equals 0 to t equals 4. So if t equals 0, then x equals what? Square root of 0, which is 0. And when t equals 4, x equals the square root of 4, which is x equals 2. So on this one, we have a parabola, x squared minus 2, until we're going to graph it between x equals 0 and x equals 2. So it will look like that. And oftentimes you're asked to give the direction in which it is traced. But when x equals 0, we're down here, and when x equals 2, we're up here. So the direction looks like that. Is that one a function? And what about b? Was that a function? Ellipse? No. All right, so you'll be doing problems like this in tonight's homework, getting rid of the parameter and determining whether the rectangular function or the rectangular equation is a function or not. Okay, that's the first part of the homework you'll be doing tonight and tomorrow. Now let's see what else we will be looking at. Okay, so everything that we've done with rectangular functions, we now, in this chapter, want to be able to do with parametric functions and polar functions. So we dealt with slope and concavity with rectangular functions, and I want to just do a little review as to what we know. So slope in calculus is equal to what? What do we call it? Louder. Rate of change? The derivative. That's the key word I'm looking for. Derivative. And how do we write, what's the notation for a derivative? There's dy, usually dy dx. We haven't moved to t's yet, but we will think about that next. We write it as y prime, we write it as f prime of x, all of those. And we used slope to determine maxes and mins. Okay, and how did we do that? We want to find where the derivative equals 0, so that's finding a critical point. Any critical point, which is where dy dx, thank you, equals 0 or undefined. All right, and then what do we do? Good. Use the first or second derivative test. which involves setting up intervals for the first derivative test around our critical points and testing to the left and right of them. The second derivative test, what's the shortened version of that? What do we do for the second derivative test?
Find the next derivative and see whether it's positive or negative.
So we find the second derivative, and at the critical point, if it is positive, then we are concave up and we have a minimum. And, what was that?
Positive.
That's right, positive is smiling, that's right. And if it is concave down, or negative at the critical point, then we have a maximum. So, just remember, when you are doing these first and second derivative tests, if the problem says justify your answer, you need to show your analysis, and then write a sentence summarizing it. The sentence could be something, quiet please, something like, based on the first derivative test, we have a maximum here. And you can just draw your attention to the analysis you did, okay? All right, now, concavity, tell me what we know about that. That is based on what? The second derivative. And if I was looking for a point of inflection, what would I do? We want to find where the second derivative equals 0 or is undefined. I call those possible points of inflection. We don't know yet if they are until we test. And then what do we do? We do that one test. You can do a sign change. That's the one you're talking about? A sign chart kind of thing? Yep, I just call it, we build some intervals around the possible points of inflection, and we check concavity on either side. And we check concavity by plugging into the second derivative. And we are looking for y double prime to change from positive to negative, or y double prime to change from negative to positive to be a POI. Okay? So a little review. All right, so we now are going to be doing this, but we're going to be starting with parametric equations. So we still need to deal with dy dx and v squared y dx squared, even though our functions are given to us in terms of t. So we need to think about how we will get back to that. So let's go figure that out. Ooh, that's not that. All right, so we are going to find dy dx given x equals f of t and g, oops, no, y equals g. So we're given a pair of parametric equations, x in terms of t and y in terms of t, and I need to find dy dx. Andrew? No? Question? Okay. All right. Well, if I take the derivative of this, I am getting dx d what? dt. And the derivative of y would be dy dt. And what can I do with those two to get dy dx? dy dt divided by dx dt. And that's all we need to do to find dy dx. So we are given two functions for x and y. Take the derivative of each. Sorry, this should be dy, let me rewrite this one. This should be dx dt. Please make that clear. That was my typo, dx dt. All right, so that is very straightforward. We just take dy dt and put it over dx dt. Okay, the next part is not difficult. How would we get the second derivative? I am looking for c squared y dx squared, the second derivative with respect to x. Well, that means I need to take the derivative of this one with respect to x. Well, it looks like a quotient to me, yes? But we need to remember we need to apply chain rule. Whenever we take the derivative of something with respect to t. So we would get, if I were taking the derivative with respect to x of dy dt, I would get what is called dy prime dt. And I need to follow it with the derivative of the inside. Well, it's in terms of t, and I want to be in terms of x, so it would be times dt dx. So when we apply the quotient rule, we need to remember we also are doing implicit in the middle of this, the chain rule. So the quotient rule is low d high minus high d low. So low is what? Dx dt. D high would be dy prime dt times dt dx. This is one of those things where we'll go through it the long way once, and then it'll be a little more clear how you can do it quickly once we're done. Everyone okay with what I have here? This is low d high minus, what's my high? Dy dt, d low, dx prime dt times dt dx. All over dx dt squared. So that's just applying quotient rule. We're going to rearrange it a little bit just so it's easy to see what we'll do each time. I see a dt dx in both terms on the top, so I'm going to factor that out in front. dt dx times dx dt dy prime dt minus dy dt dx prime dt all over dx dt squared. All right, and finally, I have a dt dx on the top. If I wanted to move that to the bottom, what would I have on the bottom? Another dx dt. So really, this is dx dt dy prime dt minus dy dt dx prime dt all over dx dt cubed. And what this is d squared y dx squared, which is the derivative with respect to x of dy dt over dx dt. So, if you look at this now, given that I'm taking the derivative of dy dt over dx dt, this is just low d high minus high d low over the denominator cubed. So it's almost identically our quotient rule, but we end up with the, instead of the denominator squared, we end up with the denominator cubed. Okay? So now, when you're asked to find the second derivative, it's just plugging in low d high minus high d low over the denominator cubed. Okay? Questions on that? Okay. All right, so now let's go see how we use it. Does everyone have this down? Okay, taking that as a yes. All right. So our next example, consider the curve defined parametrically by x equals t squared minus 5 and y equals 2 sine t on the interval for t between 0 and pi. So sketch the graph of the curve in the window -7 to 7, -4 to 4. So I believe I have it. And all right, so here is our equation. And it says put in the direction. So when I graphed it, I looked at when it was graphing which part. It starts over here on the left and goes to the right. So I'll put in my arrows. Give yourself a sketch of this, please. Then what we are being asked to do in this problem, part B, is find the highest point on the curve, justify your answer, and part C, find all the points of inflection on the curve and justify your answer. So exactly what we just talked about. So in part B, we're looking for a maximum. And let's remember, we want an x comma y for our maximum point. We do not want it in terms of t. All right? But we'll use the parametric functions to get there. So what do I need to do? I need to get the derivative in terms of x. I need dy dx. So for that, we just need dy dt over dx dt. All right, what's dy dt in this problem? 2 cosine t over dx dt, which is just 2t. Okay. I'm going to leave it like this for now, just to make it clear when we plug into our second derivative in a minute. It does, actually I'll write it, it does simplify to cosine t over t, but we will remember dy dt is 2 cosine t and dx dt is 2t. Alright, so there is our first derivative. Help me find critical points. What do I do? Yep. Cosine t over t equals 0. And where does that happen? Happens when cosine t equals 0, or if t equals? Not pi fourths. Pi half, that's it. Pi half. Okay. And where is cosine t over t undefined? Good. All right. Now in this case, t equals 0 is one of our endpoints, and we are not going to look for, we'll never be asked to find a relative max at an endpoint. It could be an absolute max, but we're just looking for a high point, so we do not need to consider the endpoint t equals 0. So the only place we really need to test is at pi half. So help me set up my intervals to test pi half. From where to where? Our domain is 0 to pi. So we'll go 0 to pi halves, and then pi halves to pi. Pick a nice test value. Pi fourths and 3 pi fourths. And what do I plug it into? Into the first derivative. Okay? So if I plug pi fourths into our simplified derivative up here, will I get a positive or a negative? I don't care what the value is. I will get a positive. And if I plug in 3 pi fourths, I will get a negative. So we get increasing then decreasing, showing we have a relative max at t equals pi halves. Am I done? Nope, they want the highest point on the curve, so they want x and y. So we need to remember x equals pi halves squared minus 5, and y equals 2 sine of pi halves. X, y is our maximum. And it says justify our answer, so by the first derivative test, we have a maximum at x, y. Okay? So that's a complete solution. Any questions on what we did for that one? Any questions? Okay. Next thing we need is our part C, which says find all points of inflection and justify your answer. Okay, we're going to do this on a separate page. Again, we remember our x is t squared minus 5. Our y is 2 sine t. Our dy dx was 2 cosine t over 2t, which simplified to cosine t over t. All right, second derivative. If we're looking for points of inflection, we need our second derivative. So now we're just going to apply that chain rule and remember that the bottom is cubed instead of squared. So low d high would be 2t times negative 2 sine t minus 2 cosine t times 2 all over 2t cubed. I'm just using the actual dy dt and dx dt to show our plugging in. You could have just applied quotient rule to this and have a cube on the bottom. That works. All right, so where is this equal to 0 and where is it undefined? Undefined where? T equals 0. Equals 0, where that thing on top, negative 4t sine t minus 4 cosine t equals 0. Is everyone okay with what I'm doing there? It's undefined where the bottom equals 0. It's 0 where the top equals 0. And this you would just put back in function mode in your calculator and graph it to find our t. And we get t equals 2.798. Now, what do I do with that? Yep, we need to test the sign on either side. So we're going to go 0 to 2.798 and 2.798 to what? I, right? All right, so test values here, maybe 1 and 3, and you would need to plug them into our second derivative. So we'll be plugging back into this. And 1 and 3 are not the easiest for us to figure out without a calculator. All right, but from our previous class, we showed that we had a negative when we plugged in here and a positive here, which means what happens at 2.798? We have a point of inflection. What is the meaning of a point of inflection? Good. Concavity changes from positive to negative or negative to positive. All right. But again, they wanted any points of inflection, so this is at t equals 2.798. So the points would be x equals 2.798 squared minus 5, and y equals 2 sine 2.798. And there's no real name for, you could say, by the concavity analysis above. We have a point of inflection at x, y. Okay? A little review on our Calc 1. All right, questions on that? Okay. All right, last thing we need to cover in this section is arc length. We've done arc length in the past. We derived the formula. And the formula in this for rectangular was the integral from a to b of the square root, oh dear, there, dx squared plus dy squared, correct? And we also wrote it as the square root of 1 plus s prime of x squared dx from a to b. Well, as you can see, with parametrics it ends up being almost identical. Instead of just dx squared, we have dx dt squared. Instead of dy, we have dy dt squared. And our interval for our integral is from t1 to t2. So if we look at the example we have here, we have x equals 3 sine t, y equals 3 cosine t, on the interval 0 to 2 pi for t, and we want to find the length of the curve. These end up being plug and chug. I will tell you, you need to be careful with your algebra. Okay, these tend to sometimes require a little more algebra. So my integral will go from where to where? 0 to 2 pi. Square root of, well, I need the x dt. And what is that? 3 cosine t. And dy dt is negative 3 sine t. That's all we need to put in here. 3 cosine t squared plus negative 3 sine t squared dt. The dt is obviously outside the square root. All right, and when we square this, we get 9 cosine squared t plus 9 sine squared t dt, integral from 0 to 2 pi. What can I factor out? 9. And when I do that, I have 9 times cosine squared t plus sine squared t, which is what? Yep. So we get the square root of 9 times 1, or the square root of 9, which is 3. So the integral that we're really taking, the integral from 0 to 2 pi of 3 dt, which is lovely. We get what? We're going to get 3t evaluated between 0 and 2 pi. So we get 6 pi minus 0, or 6 pi. And you would just say units unless they gave units. The length, so it's units to the first. So I chose this one. This one was not in your book. But this, quite often they come out nicely like this, but at other times they require a little more work. So we'll do one more example. It requires a little more algebra. Are we okay with this one? Yes, you are. It's units. It says units. You did that.
Yeah.
That almost makes me happy. Except that someone would go look at it and then come back and take a test. But I would rather have that than All right. Can I move on? We're good? Okay. All right. So our last example, this one is from your book. Find the length of the asteroid. That's kind of fun. X equals cosine cubed t, y equals sine cubed t from 0 to 2 pi. So our length will be the integral from where to where? 0 to 2 pi. Square root. All right, dx dt. 3 cosine squared t, right, times negative sine t, chain rule. dy dt, yep, 3 sine squared t times cosine t. All right, so we need to put those in here and square them. So we'll have 3 cosine squared t times negative sine t squared plus 3 sine squared t cosine t squared dt. All right, so here's where our algebra comes in. All right, we need to square this, and we get what? We get 9 cosine to the 4th t. Negative's going to go away. Sine squared t plus 9 sine to the 4th t cosine squared t, all under a square root. I can do it without running into anything. Almost. dt integral 0 to 2 pi. All right. What would you like to pull out? 9, definitely. And cosine and sine, good. Cosine sine squared t sine squared t, leaving us with something lovely. Cosine squared t plus sine squared t. So we have 9 cosine squared t sine squared t under the square root, which gives us what? 3, and it's an absolute value of cosine t sine t, because it is positive root, so it's the positive, and we're integrating that from 0 to 2 pi dt. All right, so when we get these absolute values, we always have to do a little something to figure out. Well, where are cosine and sine both positive? In the first quadrant. So I could do an integral from 0 to pi halves times how many? Times 4. And I'm going to pull the 3 out in front as well. And it will be the integral of cosine t sine t dt. All right, how do I take that integral? U sub. What's my u? I would make it sine of t also, so I don't have to deal with negatives. Du, cosine t dt. So I have 4 times 3 integral of what? U du. Okay? And that is 12 times u squared over 2, which is 6 times what? Sine of t squared, evaluated between 0 and pi halves. All right, and now we're just evaluating. 6 times sine of pi halves squared minus 6 times sine of 0, not theta, 0 squared. All right, and what do we get? We get 6. Yes? We had to deal with this absolute value, so we picked the region where cosine and sine is both positive, and then we said how many of those would get me from 0 to 2 pi. So it's positive from 0 to pi halves times 4 quadrants to get the full length.
The arc has to have the same length in the first quadrant and then all the other quadrants.
The cosine, it will, yes. In this case, because it is symmetrical, it
But
will.
that function really could.
There are absolutely functions where that would not work as well, yes. But in this one, it would. All right. Any other questions on this one? Yep, on my way. There it is. All right. Now, that's all we have. Your homework for tonight is on your assignment sheet, and there is no new lecture tomorrow. So you'll have another assignment from this section. I will be looking for a little polar practice and a little vector practice to add to the homework, just for a little reminder, okay? But tomorrow in class we'll go over homework and then you'll have homework time, okay?